Hey everybody, and welcome to the third lecture of the Chemistry 2 course, and this lecture is going to be on hydrogen, and it's the only lecture where we'll be looking at one element on its own, and this is because it doesn't really fit nicely into the periodic table. So in the following lectures we'll be looking at the S block, the P block, the D block, but hydrogen doesn't really fit in so neatly with any of them, so we're looking at its properties on its own. And in this first part we'll just take an overview, look a little bit about hydrogen, how it's produced, what it's used for, and therefore what it's important for. So as I was saying, it doesn't fit neatly into the periodic table. You see here on the right a very small periodic table, and it's usually quite often just shown in the middle at the top because it doesn't neatly fit in anywhere. Even though it's got an unpaired s electron, it doesn't really follow the trends of the other group 1 metals, especially since it's not a metal. So we just put it here on its own. It's the most abundant element in the universe, and on Earth it's the 10th most abundant by mass. This is because a lot of the compounds on Earth are organic, built up of organic compounds, and if you don't know them already, you'll see in the organic half of the course that most organic compounds are just chock full of hydrogen. It doesn't occur naturally on Earth in elemental form, so just H on its own you won't find, but it is stable under normal conditions, sort of atmospheric temperature and pressure, as dihydrogen or H2, and it's present at very low levels in the lower atmosphere, but as you get higher up and close to space, it essentially becomes the only component, and it floats up there because it's so light. So about the gas itself, it's colourless and odourless. It's got very low melting and boiling points, and this is because of the intermolecular interactions. So when we were talking about solid structures in the last lecture, one of them that we touched on but didn't go into too detail with was the molecular solids, and the example of one of the slides there was I2, like iodine in its solid form. And we said that between the atoms there's a strong covalent bond usually, but in between the molecules it's very weak, and hydrogen's a great case of this too. It's quite unreactive because this bond, the H2 bond, is pretty strong, but exceptions are reactions with halogens, and we'll focus more on these in a couple of lecture time. We'll be looking at the P block and going through group by group, and we'll be looking at the reactions of the halogens then, so we'll talk about the hydrogen halogen reactions then. So how it's produced, we'll start is on the next few slides as well. Industrially, we get most of the hydrogen we need through steam reforming, and this is shown in formula form here. So this is when we take natural gas or light crude oil, and the crude oil is usually turned into the gas. So here we've got methane as the natural gas source, and it's reacted with steam at extremely high temperatures, and you'll get this mix which we call syngas. And we'll come on to this in a few slides as well, what it's used for. This is almost the backbone of the petrochemical industry. This syngas then gets taken and used for lots of things, and it's a combination of carbon monoxide and 3 hydrogen molecules. It's done at such high temperatures, as you can see, nearly 1,000 degrees. If you remember back to when you were doing equilibrium chemistry in Introduction to Chemistry or whatever you did before, and Le Chatelier's principle, you'll notice here the enthalpy change of the reaction is endothermic, so it takes in heat, and the principle was if you apply an external factor to the equilibrium, it will shift to minimize this change. So we do it at very high temperatures because then this favors syngas production. It's also produced naturally. It's a product of fermentation and a byproduct of the nitrogen cycle as well. So all the sort of detritus and biomass that gets decomposed, and all the reactions in nature that happen because of these bacteria, hydrogen's produced as a byproduct of those. Then there are also quite a few bacteria that then use this byproduct hydrogen to do things like turn CO2 into methane or sulfates into H2S, things like this. So it's used a lot in the natural cycle of the world through bacteria. Finally, we can make it in the lab, and this is an important thing to know, like what reacts to produce hydrogen. And it's the reaction between an electropositive metal and a dilute acid. I don't like this definition too much because quite a lot of metals are electropositive. The better one is that metals with a negative standard reduction potential will react with an acid to generate hydrogen. So there are some exceptions, like aluminium, but if you look in the Chemistry Cube textbook, and also if I ever ask a question like this in an exam, you'll have a table of elements or metals and their standard reduction potentials. So all you need to know is that the negative ones are the ones that will most likely react with an acid and generate hydrogen. So what do we use this hydrogen for? Well, it's mostly used in the Haber-Bosch process, and this is to produce ammonia. So the fixation of atmospheric nitrogen is the posh way of putting it. But we take nitrogen from the atmosphere, and hydrogen that usually comes from this hydrothermal, the steam reforming process I was talking about earlier, and then they go together to make ammonia. And why this is so important is because it's used as a fertilizer, and therefore we're able to grow so many more crops, feed so many more animals. And there's a really nice figure I took here from an article that's nearly over 10 years old now, showing how much the world depends on this Haber-Bosch ammonia. So the solid black line here is the population growth of the world. You can see from the 1950s it really shot up. And this dotted line here is the percentage of the world population fed by Haber-Bosch nitrogen, and that's on the right, so nearly half of the world's population. And what they mean by this is the amount of food that we'd be able to grow without the Haber-Bosch process and without all this fertilizer. If we didn't have it, we wouldn't be able to make enough food for half of the population to survive, essentially, which is quite crazy when I think of one process having such an effect on humanity that is half of the population is dependent on it. So that, as I was saying, is about over half of the hydrogen produced is used for the Haber-Bosch process. One of the other major uses is to convert it into methanol, and there are two reactions shown here. Either we can take the syngas that we were saying about that's produced from the steam reforming and react the hydrogen and CO directly to make methanol, or we can react it with CO2, so hydrogen and CO2, to make methanol and water as a byproduct. And this is important because methanol can then be further reacted. Usually these are all on the same industrial plants. Methanol is taken and further reacted to make ethylene or propylene for plastics. Essentially they'll be polymerized to polyethylene or polypropylene. So this is at the very beginning of the process, but this is super important for all petrochemicals, as I say, going to polymers and other feedstocks. Hydrogen, so this is two other uses of hydrogen, not methanol now. In the petrochemical industry again, benzene is reacted with hydrogen in the manufacture of the nylon process. And in the food industry, there's hydrogenation of alkenes, which is used to convert unsaturated fats into saturated fats. One of these is super unhealthy for you. I can never remember which one. The saturated fats are the unhealthy ones, I think, because they're unnatural. But they're what's in loads of McDonald's and stuff, so they're pretty tasty. Finally, we'll look at the hydrogen economy. This is very important at the moment as the world's going greener and more sustainable. So the main thing is that currently hydrogen is manufactured from fossil fuels, as we saw the natural gas for the steam reforming process. But fossil fuels won't last forever, and probably an even bigger problem than this is that they create a lot of pollution, so a lot of greenhouse gas emissions, CO as we saw, but also CO2. So we need to find cleaner ways of getting the hydrogen we need, because we're always going to need it until we can find a replacement for the Haber-Bosch process, it seems. And electrolysis of water is a very clean way to do it. We take water, which is H2O, and split it using electricity into hydrogen and oxygen. So the process itself seems very clean. You just get hydrogen, the only byproduct is oxygen. There are a couple of drawbacks though. The first one is that electrolysis is much more expensive than steam reforming, so therefore it's not attractive. And it's therefore only viable when electricity comes from cheap sources, such as hydroelectric power plants. The other thing to consider is the initial source of the electricity. Not only is it only viable when it comes from cheap sources, it's actually only useful if the electricity electricity comes from renewable sources. There's no point in using electricity that's made by burning coal to split the water, because then we're still using fossil fuels, still producing a load of pollution. It's just at a different part of the process. So we need cheap and renewable sources, like hydroelectric power is good, wind power, nuclear, even things like this. And finally, as part of the hydrogen economy, is using hydrogen to replace fossil fuels in other parts. So a good example of this is hydrogen as a fuel. The specific energy of hydrogen, this is how much energy we can get out per unit mass in this case, is very high. It's 3 times higher than petrol, 5 times higher than coal, so we can get a lot of energy out of hydrogen. And this can be done by recombining the oxygen and hydrogen, say that was made by water splitting, to produce electricity, and this is in a fuel cell. But there are quite a few drawbacks. This specific energy in grams, when you look at the volume, hydrogen is a gas, it's nowhere near as high, and you'd need somehow to pressurize the hydrogen to get enough of it in the car. It's also very expensive because hydrogen is quite expensive, and obviously there aren't any hydrogen refueling stations, or at least not many of them. And the storage I've just talked about, when you think of the volume rather than mass, it isn't so good. But here's a table comparing it to other fuels. So that when we look at the specific energy per kilogram, it's hydrogen's at the top, and it's more than twice as energetic as most other fuels we can think of. But when you look at the density, so taking into account the volume, it's much less. So that's the biggest drawback.